Right, Enric, you're the next chair, so um,
Thank
stage is
you.
yours.
Hello, this is Henrik Boström, and I have the honor to be the chair of this session. And it's my pleasure to introduce the next speaker, Professor Ulf Johansson from Jönköping University, who will give a talk on Venn predictors. And Professor Johansson's research spans over more than 2 decades, and was an early pioneer in the today very popular field of explainable machine learning. So he did important contributions on the rule extraction for neural networks. And more recently, he has made significant contributions in the area of conformal and Venn prediction. And he has in particular looked at explainability in these contexts and also how to apply decision tree and forest learning in this framework. So today he will talk about Venn predictors, and this is a very important area of research from which you can get well-calibrated probabilities, which has many important applications in decision-making contexts. So I'm very glad to introduce Ulf to you. Thank you.
Okay, good morning, everyone. Thank you for the nice introduction, Henrik. And also thank you for the invitation to giving this tutorial at Coupa. So I will actually start with 2 disclaimers. Henrik Linusson only had 1. So the first disclaimer is that, of course, giving a basic tutorial about Venn predictors at Coupa, it's kind of like giving a lecture in Physics 101 with Einstein in the audience. But never mind that. I will start from scratch. And the second disclaimer is that I come from machine learning and not from algorithmic theory or computational learning theory. Having said that, while I'm giving this tutorial, it's actually based on joint work with my colleagues here in Jönköping, Cecilia Sönström and Tuve Löfström, and also with Henrik Boström at KTH in Stockholm. Before I start with the actual tutorial, I would just like to show you a picture of the beautiful city of Jönköping, where I work at Jönköping AI Lab, or Yale for short. And what you see here is the city center of Jönköping, and our campus is right in the center of that. So here we have the white building in the middle is the business school. I'm in the School of Engineering over here. We have the School of Health and Welfare here, and also the School of Learning and Communication here. So it's really nice situated right in the center of the city. To the north here, we have the Lake Vättern, which is the 2nd largest lake in Sweden. We have approximately 100,000 inhabitants in Jönköping. It's the 10th largest city in Sweden. So the outline of this presentation is that I will start talking about probabilistic prediction. I will actually give a critical look about conformal classification. By the way, it was really a stellar presentation, Henrik. Well done. Then I will move into Venn predictors, starting with the transductive case and then moving to the inductive case. Then I will cover the special case, the so-called Venn-Abers predictors. And that would be like the technical part of this presentation. After that, I would like to look into an area that is called algorithmic confidence, specifically in the areas fairness, accountability, transparency, and explainable AI. And I will take an example where we make probability estimation trees trustworthy. And we also evaluate Venn-Abers for that purpose. And I will end up with showing just 2 conformal regression trees, so leaving the Venn and the Venn-Abers framework and just showing that we can create rather trustworthy models also for regression. So that is the outline. So let's start right away with probabilistic prediction. So we know that I would say most classifiers are able to output not just the class label, but also some kind of estimation or even a probability distribution over the possible labors. And of course, for this to be worth anything, these probability estimates really need to be well calibrated. And what we mean by that in a loose sense is that the predicted class probabilities should reflect the true underlying probabilities. And if this is not the case, of course, then these predictions actually may become misleading. But on the other hand, if we have some kind of automated decision maker utilizing a well-calibrated such probabilistic predictor, and we combine that with utilities, that would actually produce optimal decisions, at least according to the Bayesian decision theory. When we talk about probabilistic prediction, the goal is to obtain what we call a valid predictor. And in general, validity is a really complex concept. And it means that the probability distributions from the predictor, they should really perform well against a number of statistical tests based on observations of labels. Here, we will focus on calibration. And simply put, calibration is that if we have a probability estimate for a certain label, then the probability for an instance, a test instance actually belonging to that class, given that probability estimate, should be equal to the probability estimate. Or even more informally, if we make a number of predictions where the highest class membership probability is, say, 0.9, then we expect 10% of these predictions in the long run to be errors. And of course, like I said, most models are capable of producing probability estimates off the shelf, but these are, I would say, as a rule, very poorly calibrated. Specifically, of course, there are absolutely no guarantees that these would be well calibrated. And if we look at models like naive Bayes and decision trees, we know that these probability estimates would be poorly calibrated. There are even more recent studies saying that even models that were assumed to be well calibrated off the shelf, like modern, that would be deep neural networks, and even traditional neural networks, they are often not. And even yet more techniques not shown on this slide, for instance, support vector machines. They typically use some kind of internal calibration, typically using Platt scaling, which I will show on the next slide. And if we look at random forests, for instance, they will typically not be well calibrated either. So while we are able to get probability estimates off the shelf from most models, those would typically not be well calibrated. There are a few approaches for calibration, and the two most well-known would be Platt scaling and isotonic regression. In Platt scaling, we fit a sigmoid function to a calibration set, and then we use that as the probability estimate instead of the raw values. And in isotonic regression, we do almost the same, but instead of the sigmoid function, we fit a so-called isotonic function, and that is, of course, a non-decreasing function. So we should also note that calibration is not all. I mean, it's easy to construct a probabilistic predictor that is actually unbiased in the large. We could just ignore all the inputs and output a prediction K over L, where K would be the number of ones in a training sequence of the size L. And of course, it's easy to construct also a multi-probabilistic predictor that is even unbiased in the small. Again, just by ignoring the inputs and output this multi-prediction. So from this, we learned that we need predictions that are relevant to the test instances. Calibration is not all. In addition, predictions must be specific, or sometimes called, they must be sharp. So before I move into Venn predictors, I would like to look a little bit into conformal classification and why we recommend the usage of Venn prediction instead of using conformal prediction for classification. So when we interpret conformal classifiers, we must be very careful, because what we know is that we will make exactly epsilon errors in the long run. And of course here, just like Henrik Linusson described, an error is when the correct label is not in the predicted label set. But if we think about that, the guarantee really only applies a priori. That is, once we have seen a specific prediction, the probability for that prediction to be wrong is no longer epsilon. And we can reason about this very easily. Let's say that we have a two-class problem. Then normally a number of the instances would get prediction sets containing both classes. And then, of course, according to the conformal prediction framework, these instances cannot be errors. Or put in another way, all errors must be made on the remaining singleton predictions. Here I'm, of course, assuming that we don't have any empty predictions. If we have empty predictions, those would be calculated as errors as well. So that this means that once we have actually observed a singleton prediction, then the probability for that being incorrect is most likely much higher than epsilon. And this is kind of counterintuitive. In fact, we only know the probability of the next prediction being incorrect or not. And in my opinion, this is a severe drawback of conformal prediction, or rather conformal classification. And I would like you to note that here, of course, that using confidence and credibility instead of the set predictions, that would not be a solution. The confidence metric there is still tricky to interpret. Henrik Linusson, who gave the last tutorial, suggested a method for actually providing accurate error probability estimates for singleton predictions, restricted to two-class problems. But even that method required having seen a number of predictions. And of course, this is a problem only related to classification. It does not exist in this form in conformal regression. So turning to Venn predictors then. I will start with the transductive case. And first, I would like to say that Venn predictors are multi-probabilistic predictors with proven validity properties. And of course, there is a general impossibility result for probabilistic prediction. And Venn predictors circumvent this in two ways. So first of all, multiple probabilities for each label are output, and one of them is the valid one. And also the statistical tests for validity are restricted to calibration. The key idea of Venn prediction is really to divide all the examples into a number of categories. And then we use the relative frequency of the labels in each category to estimate label probabilities for test instances falling into that category. And the categories then, they are defined by something that we call a Venn taxonomy. And then every taxonomy would lead to a different Venn predictor. And once we have this division into categories, then for a test instance, the category would be determined in an identical way as for the training instances. And then the label frequencies of the training instances in that category would be used to calculate the estimated label probabilities. So this is the overall or the key idea of Venn predictors. However, to ensure validity here, we must include the test instance in the calculation. And of course, we don't know the true label for the test instance. So we need to consider all possible labels. And by doing this, we really create a set of label probability distributions. So in a little bit more detail, we have a test instance here. And then we take every possible label. So if it is a 2-class problem, we would just have 2 labels. If it is multi-class, of course, we would have more labels. And then we add the example with the input vector together with the tentative label to the training examples. We find the category to which this example belongs. And then we let C of K be the set of training instances belonging to that category. And then we just use this to calculate the probability distribution. And this would be done once for every possible label. In words, for every possible label, we find the relative frequency of instances with that label in category K. So this was the original formulation of Venn predictors, and it's a transductive setting. And this could, of course, in principle, be built on top of any predictive model. The predictive model would just be used to determine the category. It would not be used for the actual prediction, but just to determine the category. And then one very basic Venn taxonomy would be to just look at the predicted label from the classification model and then put all examples predicted with the same label into the same category. However, if we do it like this, the model would have to be retrained once for each label for every test instance. So it would be kind of computationally heavy. And another problem with this is actually that it doesn't really produce one predictive model. We wouldn't get one model that we could inspect or analyze, or even for that matter, deploy it without access to the training data. So there are other settings where it makes more sense to use transductive Venn predictors. So one case would be to use it together with lazy learning, or specifically K nearest neighbors. And then one obvious taxonomy would be to assign 2 instances to the same category if their closest neighbors have the same label. And if you want to look into this more, there is an excellent tutorial from Coupas 2017 from Paolo Toccacelli, where he has a very good and detailed example of this. And we could also note that there is a direct comparison between transductive and inductive Venn predictors based on these lazy learners. And there we see that the transductive approach actually produced higher accuracy and tighter probability intervals. So in some scenarios, it can actually be beneficial to use the transductive approach. I will now move to inductive Venn predictors. And of course, the general scheme is very similar to the case of inductive conformal predictor that Henrik Linusson demonstrated. Here too, we split the labeled training examples that we have access to into 2 parts. We have a proper training set, and this is again used to train the underlying model. And we have a calibration set that is used to estimate the label probabilities. Here, the taxonomy would be based on the underlying model. And actually, for each calibration and test object, the output of the model would be used to assign the instance into one of the categories. So again, the trained machine learning model is not used for the actual prediction, only for the category assignment. And I know from experience that this is sometimes tricky for people who are not familiar with Venn predictors to realize. But again, the trained model is not used for the actual prediction, just for assigning the category. The test step here is very similar to the transductive case. So when we are presented with a new test object, we want to estimate the probability for each possible label in the label set. And for test instances, we would again first determine the category. And here we need to make sure that we do this in an identical way as for the calibration instances. And then we would use the label frequencies of the calibration instances in that category to calculate estimated label probabilities. And of course, we need to include the test instance in this calculation. And the true label is not known, so we need to consider all possible labels. And this is done in exactly the same way as in the transductive case. But of course, here, only one model is trained, so there is no retraining of the model. Normally, instead of dealing directly with these probability distributions, we use the lower and upper probability as equations here. Okay, so I got a message. My internet connection is unstable. Hopefully, it works. So we would calculate the lower and upper probability estimates, and they are defined by these two equations. And we can see that the difference here is very minimal. We only have to add +1 here when we calculate the upper, and the rest of the calculation is identical. And to make the actual prediction using these lower and upper probability estimates, we could actually do this in slightly different ways, but I would say one very common procedure is to take the maximum of the lower probability estimates and pick that label. And once we have decided on the prediction, we would output that label together with the probability interval created from the lower and the upper value. So in summary, to do inductive Venn prediction, we do these 4 steps. We use an underlying classifier and a taxonomy to divide all calibration instances into a number of categories. And then for a test instance, we find the category in the same way as we did for the calibration instances. We use the relative frequency of the labels in the category as the probability estimates, but we include the test instance with all possible labels in that calculation, leading to a set of probability intervals. And then we aggregate this into a prediction and a probability interval for the prediction. And if you would like to have a look at exactly how this is done, we can see the calibration step here, and we have the prediction step over here. So the multi-probability predictions produced by the Venn predictors, they are automatically valid. And this is regardless of the taxonomy used. But similar to the non-conformative function in conformal prediction, the taxonomy will affect both the accuracy of the predictor and the size of the prediction intervals. So it's still very important. And of course, we would like to have probability estimates that are as close to 1 or 0 as possible, and also as tight probability intervals as possible. And there we should know that we have one immediate trade-off, because the more categories we use, the more specific the predictions will be. As an example, if we have just for a 2-class problem, if we have this basic taxonomy where we put all the examples predicted with the same label into the same category, well, then we would have exactly 2 categories. So the Venn predictor would only be able to output one of 2 possible prediction intervals. So that would not be very specific. On the other hand, if we have too many categories, then the calibration will depend on just a few instances in these calibration sets, resulting in very large intervals. So finding a good taxonomy is an inherent problem in Venn prediction. But of course, there is a solution to this that is called Venn-Abers predictor. And Venn-Abers predictors are Venn predictors, so they inherit the validity guarantee of Venn predictors. They are only applicable to 2-class problems. And the idea here is to automatically optimize the taxonomy using isotonic regression. isotonic regression, of course, is the special case of binning. So it would separate the instances into different bins, i.e. categories. So it's only applicable to two-class problems, and the idea here is to automatically optimize the taxonomy. And these Venn-Abers predictors, they regard the underlying models as scoring classifiers. So when the underlying model makes a prediction for a test object, that output is a prediction score. And we interpret this as a higher value indicating a larger belief in the positive class or the label 1. And then Venn-Abers use isotonic regression for the calibration. In fact, an isotonic calibrator is fitted twice to the calibration set and the test instance. And this is done once with the test instance having the tentative label 0, and once with the test instance having the tentative label 1. And this might sound like it would be computationally heavy, but it can actually be done very efficiently. Using some equations, we have S0 as the scoring function for the calibration set with the test instance augmented with 0, and then we have another scoring function for the same set, but with the test instance with the label 1, and we input this to isotonic calibrators. And once we have done that, we immediately get a probability interval for the label of this instance being 1, and the probability interval for that is calculated in this way. And if we want to look at Venn-Abers prediction, as a summary, we say that, okay, the taxonomy is automatically optimized using isotonic regression. We assume scoring classifiers. So in the basic case, we are restricted to two-class problems. We fit an isotonic calibrator twice to the calibration set, and we do this for every test instance. And it's once augmented with a 0 and once with a 1. And then these isotonic calibrators are used to find the probability interval. And we can see this in more detail over here. So that was actually the technical part of this tutorial. Now I would like to talk a little bit about how we can utilize Venn predictors, or I would say the prediction with confidence framework for explainable AI, and in the sense or in the area of fairness, accountability, and transparency. And trustworthy AI is a term that is becoming more and more common. And of course, AI today is not used only for decision support, but automated decision making becomes more and more common. And then, of course, trust in these resulting decisions or recommendations becomes vital. So how to make AI solutions trustworthy is a key question, and it's addressed by researchers from many disciplines. And this AI trustworthiness, it's strongly manifested in two areas that are very expensive and vibrant today. So explainable AI and fairness, accountability, and transparency. And of course, these questions are not new. Reasoning about trustworthiness and similar issues, well, I mean, that was part of the expert systems way back in the 90s. But still, I would say that the last, let's say, 5 years, there has been a rapid growth regarding these issues. One concept that is almost always included when we talk about trustworthy AI is interpretability. So models need to be interpretable in order to allow for inspection and analysis, and that would be important for trustworthiness. So interpretability is definitely a criterion that we would like to meet. And of course, only interpretable models make it possible to understand individual predictions. And that would be without the usage of specialized and often very complex explanation models. And if the model itself is interpretable, then it becomes very straightforward to inspect and analyze such a model. And of course, the importance of interpretable models for user acceptance, that has been present in the AI discourse, again, since the era of expert systems. And we can also see that it is prominent in many very recent and high impact publications. So one example, of course, being the LIME framework published in 2016. There are also a number of societies that have published different guidelines for accountable algorithms. And we have one from the FAT-ML Principles for Accountable Algorithms and a Social Impact Statement for Algorithms. And they include both explainability and accuracy, of course, as vital components of accountable algorithms. But interestingly enough, they also say that one guiding question for accountable algorithms is how confident are the decisions output by your system? And when they talk more about this, they say that accountability really puts demands on not only explainability and accuracy, but at the very least to report uncertainty. And in fact, the ability for an algorithm to somehow reason about its own competence, and specifically about confidence in individual recommendations, that capability is deemed to be extremely valuable. And in my opinion, the prediction with confidence framework is really uniquely well positioned to meet these demands. So if we look at the requirements here for interpretable and accountable models, well, again, the model needs to be interpretable. So it could typically be a decision tree or a rule set or something like that. We want the models to be well calibrated, but they should also exhibit different confidences for individual predictions. And this then goes back to the property of being specific or sharp. And then, of course, these models, they need to be fixed so we can inspect them. And this would be after the calibration step in our case. So we would like a model to be fixed so we can actually look at the model and inspect it and analyze it. So then I would like to show you some experiments and some reasoning from a paper of ours where we looked into probability estimation trees and how do we make probability estimation trees trustworthy in the sense described in the previous slide. So probability estimation trees, well, they are decision trees, and decision trees have been around for, well, almost 50 years, and they are, of course, relatively accurate. They produce interpretable models, which is, of course, the main benefit of using decision trees, and they also require like a minimum of parameter tuning. The two most famous decision tree algorithms are C4.5 or C5 and CART. Decision trees in the standard format are, of course, available of producing class membership probabilities. And if we use trees producing such membership probabilities, then we refer to them as probability estimation trees. And this was introduced by Provost and Domingos back in 2003. And of course, for such probability estimation trees, the most straightforward way to get the class probabilities would just to use the relative frequency. So the proportion of training instances corresponding to a specific class in the leaf where the test instance fall. What Provost and Domingos showed was that, okay, of course, a leaf containing many training examples is a better estimator of class membership probabilities. So they suggested using a Laplace estimate instead of just the raw relative frequency. However, even if we use all the tricks suggested by Provost and Domingos, these probability estimation trees are notorious for producing too optimistic probability estimates, and I will show you some in a while. So then we could think about, okay, if we apply a Venn-Abers predictor on top of the decision tree, what would that look like, and what do we need to do? Well, first of all, we should note that, okay, the number of categories would of course be dynamic. So it would not be restricted to a specific taxonomy. So it would be dynamic for each and every tree. But at the same time, if we use the inductive variant, then all instances falling in the same leaf, they would of course obtain the same estimate. And this estimate can be determined from the calibration set. So we would actually have a fixed decision tree after the calibration set that we then could apply to all test instances. So we argue that this resulting well-calibrated model is a fixed decision tree available for inspection and analysis, and each leaf here contains a specific prediction consisting of a label and an associated confidence, or actually a probability interval. And this, in our opinion, is a very informative model. And just to show you what it could look like, so of course this is a tiny decision tree that we pruned back to this size in order to be able to show it here. But what we see in this tree, we have 4 leaves, and 2 of the leaves that I have marked green here, we see that we have probabilities very close to 1. So here we say with a high probability that instances fallen here should be classified as class 0, and the probability for this being correct would be between 98.3% and 1. And when we tested this, in this specific case, we had 22 instances falling in that leaf, and all of them were correctly predicted. We have another leaf down here where we predict class 1, and the probability interval is between 0.88 and 0.91. And when we tested this, we had actually 22 instances, including 2 errors. But maybe even more interesting is that we have 2 more leaves here where we have larger intervals, and also in this case we have one from 0.5 to 0.6. So we say, okay, we are very uncertain about the label, but we are also kind of uncertain about how certain we are, because that is what we see from that this interval is actually fairly large. And here, again, we have a large interval, but here at least we are fairly certain about the label. So again, in our opinion, this is a very informative model where we show, I mean, it's interpretable, it's specific, we have different predictions and different intervals for each instance, and it can be inspected since this tree is built after the calibration step. So we tested this using Venn-Abers for calibrating probability estimation trees. And here we compared 4 approaches. We compared using just the probability estimates from the tree, and that did not, of course, need any external calibration, so we used all the training data for generating the tree. We used standard Platt scaling and standard isotonic regression, and we used inductive Venn-Abers predictors. And of course, one of the main advantages of Venn-Abers is the ability to produce intervals. But if we want to compare it to other calibration techniques, then we need to use a single estimate. And we used a single estimate calculated in this way. And that is, of course, a regularized value where we mode the estimate towards 0.5. And if we do this, I will show you some results here. And of course, the detailed results can be found in the paper. So these results are aggregated over all the 25 data sets. Up here, we see accuracy values, and RF here stands for relative frequency. So this if we use the relative frequency for creating the probability estimates in the trees, and here we have Laplace estimates instead. And we don't need to dig into all the details here, but what we can see is that we definitely don't lose predictive performance by using these calibration techniques. So actually, all the calibration techniques improved on accuracy in this specific study. The same can be said for the ranking ability as seen as area under the ROC curve, with the exception that using Laplace estimates directly on the tree, that actually produced the best ranking ability. And this is not new. It has been observed before, and we reason about why this is the case in the paper. Here are some really, in my opinion, interesting numbers. So this is a very crude way of estimating the quality of the estimates. So this is just the difference between the prediction and the true target. And here, I mean, if we look here, for the decision tree, it is almost 17 percentage points too optimistic as an average. So, I mean, it's extremely poorly calibrated if we use it off the shelf. If we use Laplace estimates instead, as suggested by Provost and Domingos, well, it's a little bit better, but it's still 12 percentage points too optimistic. If we look at Platt scaling, it's very good. I mean, if we look at the empirical calibration here, it's very good. If we look at isotonic regression in this specific study, it's slightly optimistic if we look at averages. And of course, as expected, the Venn-Abers predictor is very well calibrated. We could also do this for log loss and for Brier loss. Both the trees and the isotonic regression would have infinite log losses for some data sets. So typically, it says that the probability for the wrong class is 1. And then, of course, the log loss would be infinite. There are tricks to avoid this, of course, but if we just run it from off the shelf, we get these kind of results. And if we look at the Brier loss instead, we see that the Venn-Abers predictor is actually overall, it has the best rank over all the data sets. And again, we should always remember that the Venn-Abers predictor has the ability to produce intervals, and there is, of course, a lot of information in these intervals. And here, it's just on the data set level, but we have a low value and a high value, and then we see the imperial accuracy here. And for a large majority of the data sets, the empirical accuracy is actually inside the intervals. But of course, for some data sets here, we end up with an accuracy, in this case, slightly outside the prediction interval. And we can see that this happens for a few of the data sets, and I have marked this in bold here in this slide. The conclusions from this study, well, it was a large-scale comparison of Venn-Abers to existing techniques for calibrating probabilistic predictions from pets. And the experiments gave strong evidence for the benefit of using external calibration methods in general. And if we looked at it, if we compared Venn-Abers to Platt scaling isotonic regression, Venn-Abers was actually always the most exact. And again, we also showed that the capabilities of Venn-Abers predictors, the prediction intervals were very tight, and the probability estimates were overall extremely well calibrated. So before finishing this tutorial, I would just like to say that, of course, we can do something very similar for conformal regression as well, i.e. we can create interpretable models that are specific to the tree, an example of what such a tree would look like. So here we have used normalized conformal regression. So Henrik didn't mention normalization, but it is of course a way of estimating the difficulty of different examples and then utilizing this in the non-conformity function in order to produce intervals of different sizes depending on how difficult you estimate an instance to be. And if we do that, we would end up with a tree looking something like this. Again, it's a tiny tree, but we can see that we have prediction intervals of different sizes. And again, we argue that this is a very informative model. We could even use Mondrian inductive conformal prediction. In that case, the Mondrian part would be that each and every leaf in the tree, or if you want to put it as each and every rule, if we read the splits from the root to the leaf and interpret that as a rule, then every rule would be valid in itself. And of course, that would also be, I would say, a very informative model. Of course, there are some problems with Mondrian conformal prediction. Most importantly, that we would need to have lots of data in order to have a sufficiently sized calibration set. So with that, I conclude this tutorial about Venn predictors. And of course, I will be happy to answer questions now or offline. And you can find my contact information here. Thank you.
Thank you very much, Ulf. If there are any questions, you're welcome to either raise your hand or put them in the chat, and I will read them. No questions so far, or is Valerie having a question? Okay, so here is the question from Valerie. Did you use plain vanilla or regularized plat?
Yeah, so yeah, my microphone is still on. Yeah, that's good. So we used the plat scaling as it was suggested in the original paper. So I guess that would be the vanilla version then.
Yeah, and there have been some improvements on that. There are some papers building on that to.
So I will just. Yeah, I think we used. I think we used the vanilla version.
Can I just sort of clarify my question? Apologies, there is a bit of like construction outside. In the original paper, there are two versions, plain vanilla and regularized version. And, I was quite interested about the plots kind of performing quite well. I mean, it's not so bad. I also had similar results when I was kind of looking into IWAPs and CWAPs, but my question is really, do we think this is like more like specific to the data sets that have been used? Because more recent versions of the kind of comparisons, especially like in the biomedical domain and also in deep learning, suggest that plot is only really performing well for the specific shape of the distribution, right? So which is like logistic regression. So it's kind of really does not perform well, or seems to be the case on the kind of other applications like biomedical and deep learning. So my question is really, how what is kind of your impression of seeing this kind of plot scaler in action?
Yeah, so I actually I had a look here in the paper to be sure what we did. So we used a basic regularized version. So in order to avoid infinite log losses. So I think it would be well the second variant then of plot scaling. And then I think the theory is that that plot scaling is, or the other way around, isotonic regression is most often better if we have enough data to support it. And in these experiments, the data sets were fairly small. So typically the number of instances were in the hundreds. So let's say from a few hundred instances to maybe 2,000, something like that. So it was data sets from the UCA repository.
Makes sense. Thank you. And my second question is, do you have code available somewhere? I mean, it would be interesting to see how one can apply these techniques to the trees.
Yeah, so I don't, like Henrik, I haven't published the code or put it into a repository. So to be honest, I think it would be like a dirty hack in MATLAB, most of the code. But yeah, I have the code and I could probably tidy it up a bit if someone wants to have a look at it.
Thank you.
Thank you. And then we have a question from Patricio. How does having unbalanced labels impact the calibration of a Venn-Abers predictor?
Yeah, that is an interesting question. So I haven't seen any study addressing that specifically. I mean, if we look at really unbalanced data sets. So I mean, the guarantees would still apply, but I don't. I haven't seen such a study looking into, let's say how tight the intervals would be or how it would affect that kind of properties.
Could it also maybe have an effect on when training the underlying model to form the categories?
Yeah. So I mean, if we look at let's say multi-class problems, then there could be some classes with very few instances, and then of course to even, depending on of course the taxonomy we use, but to even have any training instances falling into categories where the prediction would be a very rare label. So I mean it's something that should be that could be looked into more.
Yeah, thank you. And then we have a question from Evgeny. What would be the benefits of bagging of Venn decision trees?
I would say, of course, in the general case, bagging would produce. I mean, if we aggregate it into a forest, then we would probably have higher accuracy, but then we would lose the interpretability. So I mean, it would be the same trade-off as we have in regular predictive modeling, I think.
Yeah, but could there be a way of combining the probability intervals, or would this mean that you should actually only consider training a bagging decision trees as the underlying model?
But I think, I mean, if we use trees, the main motivation for using trees to start with, I would say, is to have the interpretable model. And in this case, we want the model to be fixed after the calibration step, and we really want it to be one model where we can look at the model and analyze it and so on. So, I mean, if we are looking for more accurate models, then we would probably use, I mean, random forests or neural networks or something like that. So maybe there would be a way of using bagging in a preliminary step and then somehow still end up with one tree. But I think this capability to produce one fixed tree after the calibration that we can use not only for the prediction but also for inspection and analysis is really important here.
Maybe well, the question could be related to also cross-conformal prediction. So would there be any, or has there, to your knowledge, been any work on cross-Venn prediction?
Yeah, there are papers about crossed Venn predictors, absolutely. And again, it would be out of the scope, I think, of a basic tutorial, but there are crossed versions of this. I would say again, of course, then potentially suffering from this problem that we wouldn't have just one model in the next step.
Okay, I think we have a couple of minutes left if there are any additional questions. Yeah, so here's one question from Ola. Can you expand on the discussion on Venn-Abers predictors versus inductive conformal prediction for different types of practical applications?
Yeah, so I haven't seen a lot of, I would say, vanilla inductive, inductive conformal predictions. Sorry. So I mean, my recommendation would be to use Venn-Abers or Venn predictors for classification based on the reasoning about that is kind of hard to interpret the predictions from conformal prediction. And then, of course, for regression, I would recommend using conformal prediction, typically the normalized version, so in order to get more informative models. But then, I mean, of course, you could also think about, okay, how do we handle multi-class problems in the Venn-Abers framework? And there are ways of training one class against all the others and so on, but it's slightly complicated to do that. So I don't know if it answers the question from Ola here. Maybe you can post a follow-up if I missed the question.
No, I think it's a good answer, but I mean it's quite relevant if you're new to the field to sort of say, okay, I can do conformal prediction, I can do Venn-Abers, and sort of the pros and cons. Are they, I mean, you know, small data, large data, unbalanced data, balanced data in this sense? Are there any sort of, you know, these types of, you know, practical recommendations are usually quite important to sort of get through.
Okay. So I mean, we haven't talked about the subject of the third tutorial yet, of course. I mean, conformal predictive distributions. So that is also a very interesting alternative. But I mean, at least again, my recommendation is to use conformal prediction for regression. And there are versions, if you use a model like a random forest, for instance, where you can use the training data both for training the underlying model and for the calibration, because then you would use the out-of-bag estimates from the random forest for the calibration. So in that sense, you don't need to separate the data into training and calibration. So I would say that is at least one go-to technique to use the random forest and calibrate on the out-of-bag data for conformal regression, and also using a normalization then with a good difficulty function in order to get these specific predictions. For classification, while I think that the conformal prediction framework is, I mean, it's very neat, and but it is kind of hard to interpret the predictions if you have the set predictions. You would probably say that, okay, I got this singleton prediction. That is really interesting. That is the most important one. But it might actually be that the probability for a singleton prediction to be wrong is very high. So I think that is a big problem in conformal classification. then of course, I mean, if you do conformal classification with the set predictions in a multi-class problem, then you might end up with interesting label sets. You might say, okay, we are probably, the correct answer is probably in this label set. So that is an interesting property of conformal classification.
Thank you. And Valerie also provided a pointer in the chat to a paper on multi-class Venn-Abers.
Yeah.
Obviously by himself.
No, but it's I've read it, and it's an interesting paper. Absolutely.
And also a GitHub pointer. Great.
Yeah.
Yeah. And then we have another question from Evgeny. Can we expect an improvement in feature selection with Venn random forest compared with that of a standard random forest?
Ooh, I have to say I don't know. I mean, you're the expert on random forests, Henrik, so maybe you could
Thank you very
weigh
much.
in here.
Yeah, so clearly there are different techniques to estimate the variable importance, which is typically what you use when you select features using the random forest. And either you do the permutation on each feature and then see how that affects out of bag accuracy. Or you look at some, say, internal gain of using each feature and then sum that up somehow. So I would say generally for using that approach, I cannot see that this would be very much affected. But if you would somehow affect the underlying learning algorithm when using the Venn approach here, then that of course could have an effect. Or if one say evaluates the quality of each feature on an external test set, then of course if you change the predictions of the underlying model in this framework, then maybe you can actually find something interesting and new. So that could be one interesting direction to investigate. Yeah. Yeah, while we're waiting for